And now we're finishing up Chapter 4 with 4.5, Quantitative Chemical Analysis. In this section, we're going to describe the fundamental aspects of titrations and gravimetric analysis and perform stoichiometric calculations using typical titration and gravimetric data. So this chapter is very close to my heart because I was trained in analytical and instrumentation methods as an undergrad. I continued my instrumentation work into grad school. So analytical chemistry is very, very close to my heart. It's a way to find very quantitative, precise amounts of something in a sample. Most people find it boring. I was fascinated by it as an undergrad. So yeah, I'm weird. I've always been weird. Everyone liked biochem, and I was the one that wanted my numbers and my analytical and physical chemistry. So let's start with quantitative analysis. The first thing I want to touch on is this term of quantitative. So we in the past have actually talked about qualitative. Okay, so qualitative, we don't care about numbers. We're just talking about like the properties of something, like the physical properties. Quantitative or qualitative also talks about what something is. Okay, it's like, oh, that's copper. I don't care how much of it there is, but that's copper. Quantitative has to do with the actual amount or concentration of a substance in a sample. Okay, so quant meaning numbers. As a matter of fact, there's literally an actual class that you take if you are a chemistry major that is all about quantitative analysis. So there's two that we're going to talk about in this chapter, and they're titration and gravimetric analysis. So let's start with titration. Okay, so titration is aqueous. Okay, so these tend to be aqueous reactions. And they have two solutions to them. You have the titrant, and this is the solution where you know the concentration of a reactant. And then you have the analyte, which is a solution that has a reactant that you don't know how much of it is in the solution. You don't know its concentration. You maybe know what it is, but you don't know how much of the analyte there is. Okay, so titrant, you know what it is, you know how much of it there is. Analyte, you don't know how much there is. So what you have to do is measure the volume of titrant solution required to completely react with the analyte. Okay, this is called the equivalence point. Okay, and then this in turn will let you calculate the analyte concentration. So we're going to go through it and explain what all this means. So some other things to know for titrations. We have what are called indicators that we add to the analyte solution that will make it change color at or near the equivalence point of the titration. So there's a lot of different indicators. Some of them turn pink. One of them is called phenolphthalein. There's phenol blue, there's thymol blue, there's all kinds of indicators. You just put one drop literally in your solution, and they're pretty neat. And so once you get the color change you're looking for, you measure the volume of the titrant you've used because you've reached your endpoint. So the color change happens with the indicator. Literally, it'll go from, you'll have like a beaker, and you've got your analyte in it, and you've got your one drop of your indicator, and right now it's clear. Okay, so maybe you got a little stir bar in here, it's stirring, keeping everything mixed up because you're dripping your titrant in. And then you reach your endpoint, and what happens is you would notice that your solution all of a sudden, for instance, turned purple. Then you stop your titrant and you record the volume because you've now reached your endpoint. And don't worry, we're going to look at some examples, and I believe there's a picture or two. So this is what a titration looks like. Okay, so you have a burette. Okay, so this piece of glassware here is called a burette. So if you look at it, the way that you take a measurement on it is 0 is actually at the top of the burette, and it counts up as you go down. And this is actually to make life easier, believe it or not. So you measure from the meniscus just like we've taught before. So if we look at this measurement here, okay, so we're kind of between 0.123 and 0.4. So I would call this 0.35 milliliters. So I would say, okay, this is my starting point for my titration and the burette. And then you open it up. It's hard to see here, but there's a little switch here. Okay, so the end of the burette has a nozzle. Okay, and when you open it, it's going to let your titrant drip out. And it drips into, in this case, this is an Erlenmeyer flask where the analyte is. And so you let it drip and drip until it reaches the equivalence point. You would see a color change, and sometimes you see a pH change. There's always something to tell you the reaction is complete. And when that happens, you quickly turn it off. Okay, so horizontal is off, on is parallel. Okay, so this is on, this is off. Okay, so you turn it off, and then you look at your burette and you read the final volume to see how much you displace. So normally it's like 20 something milliliters, but just because have a zoomed in one here, let's say this was a really weird titration and it stopped like there. So we look at this, we go, okay, 2.5, okay, I'm going to say that's 2.61 milliliters. Okay, so now the actual volume that we titrated is equal to this final volume minus the initial volume, okay, because we didn't start at exactly 0.00, did we? We started at 0.35. And that's totally normal. When you're filling up a burette, okay, you see he's got the funnel in there, slowly pouring in the titrant. It doesn't always go perfect, and you're like, you know what, it's close enough to 0. It doesn't matter anyway. All we care about is the actual amount dispensed. So the volume here would be 2.61 minus 0.35. Okay. 2, so 2.26 milliliters was how much we actually titrated. Okay, so this is just an example of how to read a burette. I wanted to talk a little bit about this because you don't get to do this in lab right now. Okay, I'm hoping eventually you'll get to see a lab. May not be till some of you get to organic chemistry, but you know. All right, moving on. So let's look at an actual example how we're going to do this for your homework and exams and lab and everything, okay? So the endpoint in a titration of a 50 milliliter sample of aqueous hydrochloric acid was reached by addition of 35.23 milliliters of 0.250 molar sodium hydroxide titrant. And then they give you the reaction, and we want to know the molarity of the hydrochloric acid. Okay, so this is one of those problems. Titrations tend to scare people because they look at this problem and they go, oh crap, I don't know where to start. And one thing I tend to point out is just solve for something. See what you can solve for. And if you go and read back, one of the things you should notice is 35.3 milliliters of 0.250 molar NaOH. So remember, molar means moles per liter. So you can go and find your moles of sodium hydroxide right off the bat. And this 35.23 milliliters is that burette volume. Okay, so remember the titrant, we know its concentration. And then we know the volume, we know how many moles we used. So we have 35.23 milliliters, 1 liter per 1,000 milliliters, and 0.250 moles of sodium hydroxide per 1 liter. Look at that. Now we would have moles of sodium hydroxide. And since we have moles of sodium hydroxide, what could we get next? Hey, look, we can now get moles of hydrochloric acid from the reaction stoichiometry. And when we look at that, it's already balanced. We see that we need 1 mole of HCl for every 1 mole of sodium hydroxide. And we have already made it halfway to our molarity of hydrochloric acid. The last part of molarity, we have moles. Okay, it's moles over liters. We have moles of HCl up top. So the last part is to divide it by liters. And we're told we have 50 milliliters. So let's start by getting our moles of hydrochloric acid. 35.23 divided by 1,000 times 0.250 times 1 over 1. We have 0.0088075 moles of HCl. Okay, I'm not going to worry about rounding just yet until the very end. So now the molarity is equal to moles divided by liters. And we have 50.00 milliliters. We have 1 liter for every 1,000 milliliters. Oops. So that's 0.05000 liters. So our molarity is 0.008075 moles divided by 0.050000 liters. And then we want a total of 3 significant figures because this molarity here is only 3. So that gives us a molarity of 0.176 molar. And let's see what they got. Okay, so they did the same thing. Started with milliliters of NaOH, got to moles of HCl. Same number we got, they just rounded early. Okay, and then moles divided by liters, so they changed milliliters to liters like this. This is fine too, however you want to do it. The same answer, 0.176 molar hydrochloric acid. So don't let the word titration scare you. I think the other reason it scares people is because they're like, oh no, it's an acid-base neutralization. We've barely touched on them. Notice we don't even care about the products. All we care about are the reactants, right? Like, who cares about the products? I just want to know what the concentration of my hydrochloric acid is. So the next type of analysis is gravimetric. Okay, and this is a type of analysis where a sample gets some type of treatment that gives it a change in physical state that lets us separate it from the rest of the sample. Okay, so then maybe you take the mass of the sample or the analyte that you can then use the stoichiometry to calculate concentrations. Okay, a lot of times this is done via a precipitation reaction. So remember, precipitation, you usually have 2 aqueous solutions, you put them together, you make a solid precipitate. So this is an example of what you might see in a precipitation reaction. Okay, then this is the stuff they precipitated out, then they filtered it out, and then we can weigh how much is there and do stoichiometry. Blah. So let's look at an example. We're told a 0.4550 gram solid mixture containing magnesium sulfate is dissolved in water and treated with an excess of barium nitrate, resulting in the precipitation of 0.6168 grams of barium sulfate. And we want to know the concentration by mass percent of magnesium sulfate in the mixture. Oops, that should be a subscript 4. All right, so let's break this down and figure it out. So we're given a mass of barium sulfate, so we can go ahead and start with that. One always safe place to start with any type of problem you're trying to solve is convert all your masses to moles, because you can't compare masses of different compounds, but you can't compare it by grams. You can only compare it by moles. So convert it to moles. And then you can use the moles of barium sulfate to get to moles of calcium sulfate using that stoichiometric factor from the balanced equation. From there, you can get the mass of the calcium sulfate and then do the percent, because you have mass of the sulfate divided by the sample. All right, so doing everything before we get to that last percentage part. Okay, we have our mass of the barium sulfate, 0.6168, molar mass, mole ratio, or stoichiometric factor, whatever you want to call it, molar mass of calcium sulfate. Oops. Oh, sorry. This should be mg, not Ca. Sorry. Gotta love open source books, right? So yeah, so the Ca should be mg. Don't let that confuse you. All right. So anyway, we found out that we had, let me go back a slide. Come on. There we go. That we have 0.3181 grams of magnesium sulfate in our sample. Okay. And then we were told that our whole mixture that this magnesium sulfate was from weighed 0.4550 grams. So that's where that number comes into play. So the percentage of magnesium sulfate in that sample is 0.3181 divided by 0.4550 times 100% gives us 69.91%. And that is our percent magnesium in our sample. Now, another type of gravimetric analysis is combustion analysis. Okay, so this is a way to get the composition of hydrocarbons, basically by setting them on fire. So what you do, you take a sample you know the weight of, you heat it to high temperature with oxygen, making it undergo combustion. Okay, and then you get the gaseous products. So hydrocarbons, okay, so hydrocarbons only have hydrogen and carbon. So when they undergo combustion, you have whatever your hydrocarbon is. Okay, I'm going to put CXHY, whatever your hydrocarbon is, plus oxygen. Okay, so when they're undergoing combustion for a hydrocarbon, they react with oxygen, and the products they always yield, and the only products, are carbon dioxide and water. Heat also comes off, but we're talking about the physical products. Okay, so because of this, then you can collect the carbon dioxide and water through a pre-weighed device that collects it. And then you can figure out, okay, how much did the weight go up? Now I know how much carbon dioxide I have. Now I know how much water I have. And then you can use your stoichiometry. So we're going to look at an example. But first, this is what this apparatus looks like. So you've got your sample, okay, that you're going to burn. And you send some pure oxygen into it. You've got the furnace around it, so it lights it on fire. It gives it that heat for it to catch fire. And then it makes these gaseous products. And this first tube grabs the water, okay? And the water is gaseous. It's water vapor that's coming off. So it collects all the water. And all the other gases just keep going through. And this guy grabs the CO2. And then any other gases, like if there was other air or something in this chamber, that doesn't matter. They don't get grabbed, they just keep on going through. So all we care about is carbon dioxide and water. Those are the only products from this reaction. So here's an example. Polyethylene is a hydrocarbon polymer used to produce food storage bags and many other flexible plastic items. A combustion analysis of a 0.00126 gram sample yields 0.00394 grams of carbon dioxide and 0.00161 grams of water. What is the empirical formula of polyethylene? So notice, based off this reaction, CXHY. So these are our subscripts, and you can also see how they're related here. X CO2 plus Y over 2 water. X and Y, those are the same thing. Okay. So what we need to do is take our mass of, take our mass of carbon dioxide, change it to moles of carbon dioxide, and then we can use the stoichiometry to go to moles of carbon, and then mass of carbon. Well, actually, not mass of carbon. We don't need that. We're not even talking about percent composition, so we don't need this side part. Okay, so then we go from moles of CO2 to moles of carbon. And then we do the same thing with water. Mass of the water that we made to moles of water to moles of hydrogen. And then we can do the carbon to hydrogen mole ratio like we did last chapter for the empirical formula. So we're going to go through an example. We're going to go through the math to show you how to do this, because it's a little intimidating looking at it, and I totally understand. So let's start with the carbon dioxide. So we have 0.00394 grams of CO2. That's what we were given. And to make that into moles, we use our molar mass. And then in the formula of carbon dioxide, there's 1 carbon for every carbon dioxide. So this is what it's talking about, how to go from moles CO2 to moles carbon using the stoichiometric factor. It's the ratio of carbon in carbon dioxide. So this calculates out to 8.95 times 10 to the negative 5th moles of carbon. We do the same thing for water. Okay, now water is H2O, so there's 2 moles of hydrogen for every 1 mole of water. Okay, when you do all your calculations, you get 1.79 times 10 to the negative 4th moles of hydrogen. So from here, now to do the empirical formula, remember we divide both by the lower number. Okay, so, or in this case, we're just looking for the hydrogen to carbon ratio. That works too. But yeah, carbon's the lower number. And what you find when you divide both of these by 8.95 times 10 to the negative 5th, 8.95 times 10 to the negative 5th. Remember, 10 to the negative 5 is less than 10 to the negative 4. Okay, so carbon's 1, hydrogen is 2. So the empirical formula for polyethylene is CH2. So this is one, if you're given an example, if you're given this on a quiz or a test or anything, use this example and kind of plug in your numbers. It'll work pretty well. And that does it for chapter 4. This was a little bit of a shorter week with our lecture since last week was super heavy. Make sure you do the homework, you do the quizzes, and please, 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 guys, do your replies in the discussion board. I'm starting to give more points to the replies to other students than your actual initial posts. Because I see a bunch of you just do your initial posts and you never come back to the board. You need to reply to 2 other students. Okay? Give them feedback. You know, did you like what they had to say? Do you agree with them? Do you disagree? Do you have follow-up questions? You need to do that. Okay, with that, this is the cutoff for what is on your midterm. So make sure you guys study up and start preparing. See you later.